switch positions.
Oh. You sure did. Now are you confused because you don't know where you belong? Weirdness. That's like when you go to church and there's a visitor sitting in your spot and you're like, you know that? I don't have that problem because my seat's reserved in the choir, but many people, I'll be watching people come in and people will come in because I'm standing at the back to process before mass and I'll watch people come in and they'll sit in spots that I know belong to people. And I'm like, this is going to be fun when these people show up. Oh, that's not cool.
5 years.
Wow.
When I got to my locker room on Sunday for my game, somebody's bag was in my spot. So I just grabbed it and just threw it across the room.
Oh, yeah.
I do have like my music goes in a certain place on the shelf in the choir room. And sometimes one of my choir buddies will accidentally put their music where my music goes. And I'm like every time it throws me because I'm like, that's my slot for all my books. You can't put your music where my music is because then I'll accidentally pull it. Then I'll be reading your notes and that'll be a disaster because your notes are not my notes. It's important, man. Notes matter.
Yeah.
Plus, I have all kinds of weird shorthand I use for my notes that I don't expect anybody else to be able to understand. All right. Are we ready? All right, well, we'll just roll a few minutes early. That way, those of you who drive can scoot a few minutes early, and if you don't drive, that's fine. You can just wait. It's not a big deal. I'll get lab cleaned up faster, too. All right, so we're talking a lot about our titrations today. We did a titration today, but we did it sort of atypically because we used a dropper, and typically we're going to use a burette. You used a burette, I think, what, 2 weeks ago? And now you'll be, or not last week, actually, and you'll be using it again in 2 more weeks. So what is a titration or a neutralization reaction? I'm sorry. What you get for me, Caitlin?
The ions that characterize bases to form water molecules in the salt.
There you go. So when an acid and a base mix, the acid's going to do what with protons? To the base. What does the acid do? How is an acid described with protons? There you go. It's going to donate protons to the base. And that's called your neutralization reaction. So there are 4 ways this can occur. And it depends on the relative strengths of the acids and bases. You can have, this is obvious. You can have strong acid, strong base, weak acid, weak base, strong acid, weak base, weak acid, strong base, right? 4 different combinations that you can have. The final pH of the solution is going to depend on whether the excess ions at equilibrium are due to a weak acid or base combination or a strong acid or base combination. So it depends on what you're putting together. If your acid is hydrochloric acid and you're working with sodium hydroxide, it's completely different from working with acetic acid and sodium hydroxide. Acetic acid is far less acidic, right? Same thing if you're working with sodium hydroxide and maybe sodium bicarbonate versus if you're trying to work with hydrochloric acid for each of those, sodium bicarbonate is a far weaker base than sodium hydroxide. What's sodium bicarbonate? Baking soda. So first option, strong acid, strong base. The only important ions are which 2? All the others are spectators. Which ions do we care about when we're dealing with acids and bases? One of them is in the name of almost every base. Yeah. Okay. You're dealing with an H+, which is your hydrogen, or your hydroxide, which is your OH negative. Remember that most of your bases are going to end in the name hydroxide. They don't all, but it's a dead giveaway if it ends in hydroxide. You know what you're dealing with, right? All right. So what 2 things are always created in a neutralization reaction?
Water and salt.
A water and a salt. Sometimes a gas, but always a water and a salt. The water comes from the hydrogen plus the hydronium. Hydroxide. If you put hydrogen and hydroxide together, you have 2 H's and an O, and the signs cancel out. You have H2O. The salt comes from whatever your other components are. So there's where you get your water, and your salt is whatever other components there are. If you're using hydrochloric acid and sodium hydroxide, you have a Cl and an Na. So they go together as NaCl, which is, what kind of salt is that? Table salt, your salt that you toss on your food most of the time. Yep. All right, so these reactions proceed far to which side? Right or left? Think about it. Yeah, right. James is pointing instead of speaking. Yes, they proceed very far to the right, which means that it favors the products, right? And then lastly, what's the pH in a neutralization reaction? What are you going for? 7 is what you're going for. All right. So here's an example at the bottom of kind of how that works out as far as if you were doing calculations. We don't need to do that calculation, but know that that calculation exists. So that was strong acid, strong base. What do you have a strong acid, weak base? So the strong acid, how do strong acids dissociate? How would you describe or categorize their dissociation into ions? Somewhat, very little, totally, slightly, completely. Oh boy, we have a debate. Okay, who says slightly? Who says completely? Yep, there's your clue. So your strong acids and bases are going to go completely dissociate. They're going to give off strong acids are going to give off all of those protons, right? All your H pluses are going to dissociate from the acid itself into solution. The product will be the conjugate acid of the weak base. And the net ionic equation involves the what transfer? From the strong acid to the weak base. What's getting transferred from the acid to the base? There you go, protons. Protons are getting transferred. Yeah. Ah! There you go. It just needs me to unplug and replug. I don't know why. It's picky. Yeah. I don't even know what does it. Bling. Come on. What do you know? There it is. So what's this? That 3 should be a subscript. I don't know why it messed up there. But what's this little guy right here? This little ion. What is that? H3O. Hydronium. And hydronium is going to form spontaneously from water alone. But if you add it with the base, it's showing here that this is because that proton that popped off the acid is going to combine with the H2O, and now you're going to have H3O. So your strong acid dissociates, which means half of that salt component is there, and then the H plus, and it's floating around, and it's going to combine with the H2Os to make H3O, and you can mix it with that base then. That's what it's showing here, the H3O plus the base in aqueous. And then you can also get the H2O plus the base with the hydrogen added to it. That's what's meant by your conjugate acid of your weak base. And if you were to work it out, it would look like that. So now we have the weak acid strong base option. So the strong base dominates the reaction, leaving what? What happens? Anybody know? So it's going to leave the conjugate bases of the weak acid in solution. And the reaction produces the conjugate base of weak acid, which can slightly react with water. And then what does it generate? Bases generate, Caitlin? Oh, yeah, there you go, Caden. Hydroxide ions, right? There's your OH negative. And what's the pH here? So your pH in this case is going to be greater than 7 because you have a weak acid and a strong base. So that means basically when the acid has done everything it can do, ion for ion, once all of those ions are worked out, you're still going to have some left over because it's some hydroxide left over because it was a strong base. So you get some hydroxides that just kind of continue to float around. So you get your pH greater than 7 because it is still slightly alkaline or basic. Does that make sense? If it's a strong base and a weak acid. So then that would mean with your weak acid and your weak base, you're going to see the opposite, right? So unlike, I'll give you that one, strong acid, strong base reactions, weak acid and weak base do not completely neutralize each other. If a weak acid and weak base, they don't completely neutralize. They just kind of piddle around, actually. Meaning the reaction reaches an equilibrium where both the acid and base remain partially, ionized, partially ionized. Yep. So they don't dissociate completely, therefore they are partially ionized. You have some hydroxides and some hydrogens floating around, but not all that could float around based on the composition of your acid and your base. The pH of the resulting solution will depend on what? Do we know what it depends on? It's going to depend on your relative strengths of your acid and your base, meaning if the acid is slightly stronger, the solution will be slightly acidic, vice versa. Does that make sense?
Yeah.
All right, there you go. Now, if you were to graph it, it would look like this. So you got volume and pH. So you've got a strong acid, strong base. You can see that as you add more acid to your base, your pH just drops. And if you keep adding acid, it's going to continue to be low. But right here is where you're neutralized. If you look at the strong acid, weak base, that spot is not so obvious, is it? And it's a little more obvious with your weak acid and strong base, and a little less obvious when you're weak acid, weak base. So when you're dealing with weak bases, that point is a little less obvious. All right, titration setup. So you kind of did this today, but instead of the burette, you used a dropper, right? The thing that's so great about the burette, you remember last week we had that tiny little 50 milliliter beaker, and I said, this will fill this entire big tall burette, which means because it's so narrow and it's so carefully and precisely graduated, your measurements are very granular, right? You'll never get as exact a measurement from a beaker as you will from a graduated cylinder. And you'll never get as an exact measurement as you would from a burette versus a graduated cylinder. Like your burette is going to be your absolute most granular measurement. The thing with the pipette is it's real hard. You'd have to like let it go every time and then watch where it is. You can do it. Like you can start an initial volume and a final volume. The problem is it's a little harder every time to kind of stop and see where you are, but you can. If you have a nice narrow graduated one, you can do that. A little harder to control though, because it's difficult to control the exact size of the drop, whereas the burette, the exact size of the drop is going to be the same every time. So let's talk about titrations in general. So this is an analytical method in which a standard solution is used to determine the concentration of an unknown solution. And the way this works is your standard solution, the one that you know the exact concentration of, is in your burette. And in this image, it's blue, and we call it your titrant. And that's what goes in your burette, and you know the concentration. So the ways I know the concentration is either I ordered it from the lab supply with that concentration, or I made it beforehand and I know it to be right. You could do it yourself as long as you know that you're doing it right. Then at the bottom in the flask, you have what's called your analyte. And when you start mixing in the titrant, it becomes your titrand because now you're adding titrant to it. It's called an analyte because it's unknown and it's what you're analyzing. So if you can remember that you're analyzing your analyte, then you know your titrant is going to be what's in your burette because those are your options, analyte and titrant, right? So you don't know your concentration of what's in your flask. So it's your analyte because you need to analyze it. So now we have something called equivalence point. Does anybody know what that is? Jordan, what you got?
It's the point when the acid and base hold neutralized.
Yes, so it's a point at which equal amounts of hydronium and hydroxide have been added, and it's determined by your color change and your dramatic change in pH. But then we also have something called an endpoint, and we'll talk about that in a minute too. Your titrant, is your titrant your known or unknown concentration? Everybody, it's your known concentration. So it's your substance known as, it can be a reagent solution, and it's known, precisely known. That's why it says it's a standard solution. It's a standard you're comparing against, you know it. And that's what a standard solution is. Any chemical solution which has a precisely known concentration or molarity. Oh, here's our buddy. We're gonna watch him in 1 second, but he's gonna talk a bit about equivalence point. Equivalence point is the point where precisely enough base has been added to neutralize the exact amount of acid in the solution. So here's our buddy Dave. Oh, in a commercial. Yay, go to school, be educated, fun. Buy toilet paper. What?
Sparkle is here to save the day.
Thanks. Toilet paper fairy.
Professor Dave here. Let's talk about titration. Acid-base titration is a way of determining how much acid or base is present in solution by determining the precise volume of acid or base that will completely react with it. It's like a kind of stoichiometry. On a titration curve for an acidic solution, pH is plotted against the volume of base that is progressively added. As we add base, the pH slowly rises, then sharply rises towards the equivalence point. This is the point where precisely enough base has been added to neutralize the exact amount of acid in solution. When we perform titrations, we recognize the equivalence point by using something called an indicator. This is a substance that will turn a vivid color once the equivalence point has been reached. When we neutralize a strong acid with a strong base, the equivalence point will be 7. If either or both species are weak, this number will vary. For example, let's say there's a solution of sodium hydroxide and we want to know its concentration. Say we react with 3 molar sulfuric acid with 25 milliliters of the base, and we find that it takes 11.6 milliliters of acid to reach the equivalence point. If we convert to liters and then have conversion factors for the concentration of the acid and then the stoichiometric ratio, we can arrive at the concentration of the reactant. Let's check comprehension.
Bum, bum. Yes. All right. So here's where we can talk a little bit about endpoint and equivalence point. And this has to do with, you can see it in the range of your pH indicator. So Team No today, for example, got a barely pink. That would be right here. They were way down here at the bottom, right? And some of you overshot and it went bright pink. There is a range for every one of these indicators. And if you look, the range is in a different place. And it's in a different place for a reason, because what happens is, say you're working with acids and you know that whatever you're dealing with is going to be very acidic, but you want to know the pH. See your range right here? This isn't going to do you any good if you're working with bases, right? Like, what would be the point? No point. But this one right here has a giant spread, a huge range where it's in between. Methyl yellow and methyl orange, we do use methyl orange in some lab. I don't know which one, but I have it, so I know we use it in some lab. But as you can tell, it has a very small range, right? Very small range. Phenolphthalene's range is a little bigger, so it's great when you're learning how to titrate. Like, it's perfect to learn with because of this range. Last week, we had bromothymol blue in the little flasks, right? And we had Emerson and Lucy blowing bubbles into little flasks. One of them had just blue dyed water in it, and the other had water in a tiny bit of base, and then it had some bromothymol blue, which made it look the same as the blue water. And as they blew bubbles into them, the blue water did nothing, but the bromothymol blue started to shift. And so she shifted it from a pH of a little over 7 to a little over 6, because she made it go yellow, right? She kept blowing. She was producing carbonic acid by blowing bubbles into that water. So you can see how this one has a smaller range, but that phenolphthalein has a good range, so it's good. Now, there's this great wiki how on how to do titration that I happened upon, but it has some issues. So let's see if you can spot some of the issues. So we'll go through it slowly because I really want you to understand all of the different steps of the titration, because some of them I do before you get here, because it just takes too long. Like today's lab took too long and we weren't even doing this. And if you had to do all these steps, you'd be here for a year and a half, and I love you, but you got to go home at some point. So it talks about getting your stuff ready. Now it has something here that we didn't have when we used the burettes last time. This is a hot plate, but you can turn it to set just the magnetic stirrer. The benefit to that is your hand's not in the way and you're not swirling a flask endlessly below a burette. So what'll happen with these titrations is it'll be like today where you had the dropper going and you were swirling, except in this case, you're doing it beneath a burette and you're just letting it drip and, you know, spinning it around slowly forever. But if you have a magnetic stirrer and you can align it properly, it saves you that problem because then it stirs for you. So let's make sure we can name all these things. So this is our hot plate. What are these two things? What are they called? Beakers. What's this thing called? What kind of flask is it? Erlenmeyer flask or conical flask? What's this thing called? Burette. What's this thing called, do you think? Burette clamp. And then this is a ring stand, but when you add the burette clamp to it, you can now call it a burette stand if you so desire. Now, it says over here, you need to rinse and purge a burette. This is very, very important. So it says to get an accurate reading from your titration, your burette must be completely clean. Caden asked me last week why I kept running water through them. I was just cleaning them after the lab. I have to clean them again before lab every time you use them. It takes me a good hour, sometimes hour and a half to prep when burettes are involved before you even get here. So you have to purge it completely of any solutions remaining from previous use. So you got to close the stopcock and fill it with water. Now, deionized water, which is the same thing as distilled water. Why are we using that instead of tap water? PJ.
Because those particles in tap water that could stay behind and mess up with the.
Yeah. What kind of particles are we worried about? Caden? Minerals, maybe? Ion. What did you say back there? Fluoride. Fluoride is an ion, is it not? Ah, do we have things like fluoride and chlorine and stuff like that in our water?
Yes.
Can we have ions in there that are either positive or negative?
Yes.
Is that going to potentially screw up our titration if it's not exact? Yeah. So these are so precise that tap water versus distilled water will throw it off. So how do you make distilled water? What does distilled mean? Do you know, Jordan?
Yeah, it's boiled to separate it from the ion.
Yes, you boil the water, it turns to water vapor, it's brought up to a point where it can cool, and then it is collected. Now, I think I showed you guys, didn't I show you guys that Moonshiner video with the guy with the still? Yeah, okay, it's the same way they make distilled spirits. So liquor that's not like beer or wine is distilled. So things like vodka, rum, tequila, these are distilled. So you take whatever your mash is, whatever you're making it from, like let's use vodka for an example. What did they use to make vodka? Do you know? Potatoes. Okay, so you take your potatoes and you throw them in with water and you chunk them all up and maybe you add a little sugar, maybe, depends. But you chunk it all up and you leave it, and then what happens? What happens to something? It'll ferment, right? Yeah, usually there's going to be some yeast or something that gets in there, gets involved, and it starts to ferment. And then that produces alcohol. So how do you separate the alcohol from the potato sludge? So you heat it up, and the alcohol is going to evaporate faster and at a lower temperature than the water because its vaporization point is lower. So it will go up and then it goes through what they call a worm. Remember, it's like a big, I showed you a picture of it. It's a big coil and it cools as it goes, right? So you have this big coil and it'll cool down that vapor, the alcohol vapors, and drip them out the end into a little cup they're collecting in, and that is straight alcohol. But you have to be careful because there's different types of alcohol produced at different points. And one of them will kill you. The other one will not kill you. The other one will kill you. So you have to know when to swap out your little cup. Like you got to know what you're doing. It's a dangerous process. But does anybody want to drink that straight? Ethanol is what that is? No, God, no. That's like Everclear or whatever. That stuff is like really high proof. So it's very, very, very high percentage alcohol. That's terrible. So then usually they put it back with water and other flavors and things like that. So the same thing is how water is distilled, is the same process. You evaporate it, you catch the vapor, you cool the vapor. Now you have water that is 100% pure water, right? It's nothing else. It's just water, no ions. Now it says, repeat the rinsing process 3 times with water. And then the way I do mine is I'll do tap water a couple times and then I'll run distilled water through it several times. And then it says, after you've rinsed the burette with water, perform the same rinsing process at least 2 times with your analyte. But there's a problem. That's wrong. This WikiHow is wrong. What do you suppose that should say? Not your analyte.
Your, titrate.
Your titrant. Yes, you want your titrant in it. Why am I going to fill my titrant in my burette and drain it out and fill it and drain it out and then fill it again before I use it? Why am I doing it, Caden?
To get there, so instead of having like left behind ions from tap water. it's
Left behind
left
water.
ions from your hydrant.
Yeah, if I've run it through with distilled water several times, I know there's no random ions in there. But if there's still little drops clinging to the side, surface tension all over the glass, clinging to it all the way down, and I add my titrant to it, well, now I've diluted my titrant, right? Even that bit, that just a few drops is enough to throw my whole experiment. So I have to run the titrant through it a few times before you can actually use it. After you've run it through a couple times, you've gotten rid of any of the diluted stuff and you're just left with your absolute known concentration, which is what you want. All right, so that's important. And usually I do that for you. The next time you see the burettes out, I will have done that for you because it takes too long and boy, is it messy. Oh, it can cause problems. So then it says you're going to clean and rinse all your glassware. So here they have their flask. What's going in the flask? What's the solution called? It's the unknown, your analyte. You're analyzing your analyte. So your analyte is going in there because that is what you are analyzing. So once you've rinsed and washed your glass and then done distilled water on this flask as well, then yeah, you can put some analyte in it, turn it all around, right? And pour it out. And it's serving the same purpose as purging the burette with your titrant, right? You don't want any random water anywhere because it messes things up. So it says if you don't have deionized water, tap water will work. It'll work, but it can throw it. It really can. However, the distilled water rinse will still be necessary as this lowers the chances of contamination of your analyte. So I usually wash it with tap water and then rinse it with distilled water. So now it says you're going to fill your burette with your excess titrant, and it should be in a liquid form. Duh. You don't want it in a solid form. Do you remember 2 weeks ago when I had the sodium acetate pentahydrate that we made that look like hot ice is what they call it? It went solid. There's a way to do that using a burette, and you put it in the burette and then you put a little distilled water on top so it's not disturbed. And then as it comes out of the burette, it makes this great stalagmite and it's really fun. I tried it one time. I will never try it again because my burette got tapped and that's just enough. And it's solidified inside the burette, which was not fun. And the only way to clean it is to use a burette brush, which is a big, long, like a spring cable kind of thing with little brushes on the ends that you got to jam down. It's a pain. Kind of, but it's flexible so that you don't jam it in and then crack your glass. Is the straw cleaner flexible? The ones I have are not so flexible. This is real bendy.
Yeah.
Oh, okay. The one I have is kind of solid, but yeah, like a pipe cleaner, kind of like a pipe cleaner, but it's got a brush on it that has nylon bristles so that none of it flakes off and gets inside. It's a real flexible little springy thing. But it says if you overfill your burette, open your stopcock slightly, let the titrant flow out till it reaches 0. You can start at the 0 at the tippy top of burette, or if you anticipate you're only going to need a small amount, when we used them last time, I think I filled them up to 30, so they had 20 mils in them. So as long as you're starting at a nice round number that you can do math from, that's the point. It's goofy to start in the middle unless for some reason you have to. So it shows you how to clamp it. Ours are different, right? Ours have the little spring lever. These are, you may see these if you do chemistry in college, and they come in from the side. You pull them out from the side and slide them back. Leave that to your brother. Yeah, he's doing chemical engineering. You can do that. So
When I need help with chemistry.
there you go. There you go. Well, that's good. He's a good resource. So I did notice though in this photo that their stopcock is not perpendicular to their burette, which means it might actually be dripping right now, which is kind of dumb. Whoever did that graphic missed that point, right? So you have to be careful when you set your beaker up and your burette, your flask and your burette. You want a space between them. You don't want your burette down inside your flask. And you don't want it too far off to the side because you don't want to drip down the side. You want to go right in the center, which is again why the stirring plate is the magnetic stirring plate is so much better than this, because this changes that relationship every time you move it, right? So now here's another important point. Tap your burette to remove any air bubbles. Why do we care? What are we measuring from the burette? What type of a measurement is it? Volume. Does air take up space?
Yeah.
Yes, air has volume, right? And it said in our lab that a typical burette drop is somewhere between 0.05 and 0.1 mils. So a little bubble of air can throw everything by one drop, which when you get into these more advanced calculations is enough to throw everything off, like ruin it. So you got to get all the air out. So you have to tap at it. Sometimes it doesn't want to move. It's not fun. And then, now this one I love too. I have an issue with this one right here. Number one, under conducting your titration. Measure out the precise amount of analyte in a clean beaker or flask. Wrong. Why? Why, Caden? I would definitely say that's the case. Can you imagine trying to, this is a 50 milliliter beaker. You want to measure 6.44 milliliters? Anybody want to try that?
No.
No, no. You want to use a graduated cylinder, or the other way to do it, and this is, I think, the way we do it in lab, is we have our analyte in a separate burette. So you have two burettes set up. This is very often how it's done. One has your titrant, one has your analyte. You use your burette to measure the exact amount of analyte because it's very, very precise, more precise than you're going to get with your graduated cylinder. So this is just goofy. Like I saw that and went, like, that is just really dumb. Who does that? Nobody does that. So measure out your precise amount. If necessary, rinse the analyte into your beaker or flask, thus making sure all the analyte is in the beaker. We talked about that. And the amount of analyte you need will depend on your experimental design, and it's different. Every lab is going to be different. Then you add your indicator. Now, it says drop a small amount of indicator into a beaker. How do you know how much? Well, many titrations require the addition of a color indicator. The specific type will depend on the titrant that you're looking for. Likewise, the amount of color indicator you will need will depend on the volume of your analyte, generally between 3 and 5 drops for 100 milliliters. So you guys did 50 milliliters last week. How many drops of phenolphthalein did you use? 2. And then today you were working with, what, did anybody even come close to figuring out what the volume of their analyte was in the little flask? Did you? They were 50 milliliter beakers. And you put in 150 drops. Did anybody figure out the volume of a drop based on calibrating your graduated cylinder at the beginning?
No.
Colin was supposed to, but he couldn't figure out that.
Oh, okay, all right.
It's about,
It was a lot. Yeah,
it's about
a lot of math.
It was a lot.
milliliters if I had to guess.
How many? 20 maybe? I think looking at them, it was probably a little less. It was probably about 10 maybe 15. Did you?
8.72.
8.72? Was it really? Okay, looks like more than that. So, okay, maybe you're right. All right. So he did get it. He did get it. I think you're the only one that got it. So it was 2 drops was recommended for that much. So you need 2 drops to get where you're going. But when you get closer to 100 milliliters, is 3 to 5 drops of your indicator. So it's going to talk here about a buffer solution, and we're going to talk about buffers, but buffers resist pH changes. So sometimes you add a buffer, and that just depends on the design of the experiment. I don't think we're doing it when we do it in 2 weeks. I'm pretty sure we don't add a buffer, but it says add a second chemical when necessary, and they're talking about the buffer. While not all titration experiments require a second chemical, some do. The second chemical is sometimes referred to as a buffer. If the titration requires a buffer, you use the pipette. And basically, it's going to resist the change in pH for a bit. which depending on what you're doing can be helpful. So then you agitate it. So you can do this with your hands. Like I said, you can swirl away, or you can throw it on a stirring plate like this. So it says, if you have one available, use one. And turn the plate on slowly, let it stir. You'll leave the stir plate on until your titration is complete. And if you do not have a magnetic stir plate, you can agitate the beaker by hand by swirling it 4 to 5 times before placing it under the burette. So swirl it, stick it, and then once it's under, you're swirling. If you're doing this, if you're using the magnetic, you can put a piece of paper on top. It will not affect the magnetic effect of the stirrer, and you'll get a better background to judge color change on, which is very helpful. You can put it on and put a little piece of paper, and then you can watch it go. Okay, now, this is kind of the distance you want. And since this is coming up in a couple weeks, keep this in mind. So you're going to put your beaker under the burette. Burette should be centered over the beaker. Tip should not be touching any of the beaker walls. You don't want it dripping down the sides. Why don't you want it to drip down the side?
Because it'll take longer to get to the thing, and it might like leave some of it behind on it, and you won't get it.
There's your big one. Yeah, those are the 2 main points. It might be the final drop that you need for your color change, but it won't all get in, and then your next drop will overshoot because some of it will still adhere to the side, and you won't have known it was your last drop because it takes forever to dribble down the side, right? So you're going to let it drip. You've seen how to do this because you've done it, but what you did was measure an exact amount. What you do in this case is you let it drip, and you have to keep your hand on it the whole time. Because as the color is being produced, it does that thing, where it flashes pink and then goes away and flashes pink and goes away. You've all seen it now, right? Everybody's seen it. So you got to do that. And then as soon as you notice it not go away, you have to stop it. So really, sometimes the best way to do it is to turn it up so that it's got a pretty steady rate of drops. And when you see it taking longer, not much longer, but a little longer for that pink to disappear, then you're going to slow that rate down so that your drops are very, very slow. And it allows you time to stir in between, especially if you're doing it manually, because otherwise you overshoot. And overshoot is no fun, but it's not the end of the world. So this is why burettes are so great, because they're so granular. So you can record your final volume from your burette. You've already got your initial volume, right? So once you've reached the end point of your titration, as soon as you see the color change, you close the stopcock, report the final volume of your titrant in the burette, subtract the final from the initial, and now you know exactly how much of your known concentration was required to neutralize the exact volume you already know of your unknown concentration. I don't know why they're throwing away a perfectly good beaker. I'm very confused.
Yeah, I don't know. Do they want you to use the trash can?
I don't want you to use the trash can. That one was, yeah, use me. It sounds like something twisted from Alice in Wonderland. Like, use me, drink me, eat me, use me. I don't know what's going on, but.
That is the one.
From 7 to 1. Oh, no, this is part 3. Finishing analysis. Yeah. So dispose of chemicals and use a labeled waste container. Okay, we always do that. Once you have, I don't know why they're disposing of your glassware, but and I love this. I love this sentence. Once you've completed your titration, empty out your beaker, your burette, and any other glassware you used into appropriate containers. That's not the container I would choose. The burette's in there. Just so you know, these are like, if that's it, that looks like about a 400 milliliter beaker based on that hand. I don't know why you'd be using that in this lab, but those are between $5 and $10 a piece. The burettes are about $30 each. Why you'd be throwing one away, I do not know. So yeah, that's real. So yeah, we have $240 of glassware out anytime the burettes are out. So keep that in mind. That's where your lab fees go. There you go. So again, you're going to clean it again, rinse it again, rinse it again, rinse it with distilled water. Unfortunately for your burettes, I don't have an easy way to dry them.
So they took it out of the trash.
Yeah, that's what they did.
Yeah.
They absolutely pulled it out of the use me trash can and then rinsed it in a very strange sink. That doesn't look anything like a lab sink. I'm so confused by it, but hey, there are dishwasher glassware washers that are tall enough for your burettes that like big universities might have, but I don't have them. So mine just have to air dry. And it makes me sad because I like to heat dry my glassware so it doesn't get spots, but whatever. So I have to like be extra careful with the burettes every time. But then you can do this calculation. So it says calculate the concentration of the titrant. Every time a titrant, titrand, remember, is the titrant plus the analyte. So it's their titrant and your analyte together is your titrand. So every type of titration will require a different calculation to determine the concentration of titrand in your analyte. Perform your titration calculations or check a titration curve for specific titrand to quantify your results. Calculations of the concentration should be done to the appropriate number of significant figures. Always figure out what that is. So there you go with your good WikiHow with some really strange choices in the graphics. Really strange and using the wrong word in the wrong place. So we're back to this again, the range. So how do we select the indicator we want to use? We have all these indicators. We have bromothymol blue, phenolphthalein, litmus paper, and methyl orange. And then we also have universal, which isn't listed here. But we have all those at our disposal. So how do we choose what we want? Well, it's your transition range that matters. So indicators do not change color at precisely one pH value. They have a specific range over which they change color. And the range is different for each indicator, which is what we were talking about. Transition point of an indicator is defined as the point at which the acid and the alkaline forms of the indicator exist in equal concentration points. So these are your zones, your ranges. So that matters. Now, we talked about equivalence point. Now we got to talk about end point. So this is a point in a titration when the indicator shows that the amount of reactant necessary for a complete reaction has been added to the solution. The main difference between equivalence point and end point is that the equivalence point is a point where the chemical reaction comes to an end, while the end point is the point where the color change occurs in a system. So your equivalence point and your end point, we'll look at them on a graph in a minute and you can kind of see where they go. But your equivalence point is going to be lower than your end point if you're looking on your y-axis on your graph. All right, so here's an overall summary of indicators. All right. I've heard that's not a great degree to get, but whatever works. Okay. All right. Yes, yes.
Also ways to determine
I don't know why it
pH
wants to
quality.
start there.
While it
Here we
is possible to quantitatively measure the pH of a solution using a device known as a pH meter, there are also ways to determine pH qualitatively. In this lesson, we will learn about indicators, which help us indicate the pH of a solution. An indicator changes color depending on the pH of the solution analyzed. Because of this, they are also known as pH indicators. Universal indicator is very versatile as it can measure pH across the entire scale from 0 to 14. It is not a single indicator, but rather a combination of various indicators. If you look at the color changes of a universal indicator according to the pH of a solution, you will find that it resembles a rainbow. If a universal indicator solution turns deep red in a solution, it means that the solution is strongly acidic, with a pH of 1 to 2. If the universal indicator solution turns green, it means that the solution is neutral, with a pH of 7. If the universal indicator solution turns dark blue or purple, it means that the solution is strongly alkaline. Universal indicator paper works in exactly the same manner. Litmus is another indicator commonly found absorbed onto paper as litmus paper. Blue litmus paper turns red under acidic conditions, pH less than 7. Red litmus paper turns blue under alkaline conditions, pH greater than 7. Phenolphthalein is an indicator commonly used to determine the endpoint of a strong acid, strong alkali, or weak acid, strong alkali titration. It goes from colorless to fuchsia pink, at a pH of 8.2. Methyl orange is used to determine the endpoint of either a strong acid, strong alkali, or strong acid, weak alkali titration. It is red at a pH lower than 3.1 and yellow at a pH higher than 4.4. In conclusion, indicators are substances that change color at a certain pH. The point at which an indicator changes color is known as its endpoint, which can be at any pH. Common indicators that you will encounter are universal indicator, litmus in the form of litmus paper, phenolphthalein, and methyl orange.
So last week, if you remember, before lab, I had, I think it was Eunice, who held some test tubes for me. And I put universal indicator in them. One was water, one had acid in it, one had a base in it. And you could see one was purple, one was red, right? And then the center one that was just the water was neutral and it was green. If you're careful, you can set up a test tube rack. And it's a great trick that you can set up a test tube rack and you can very carefully set up your test tubes with pH that goes nicely along the scale or as close as you can, and then add your indicator and watch the rainbow form, which is kind of fun. This one is really interesting. And partly I saved it for you guys just for the aesthetic because it's gorgeous. It's really pretty. So what this guy has done, and he'll explain it to you too, but he has a setup here where he's put universal indicator in here, and based on that color, it's going to be what kind of pH? Acid base, that's acidic, right? And then over here where you got the purple, it's going to be basic, right? Now, if you look, he's got glass tubing connecting all of those flasks, those round bottom flasks, which are upside down, and then this special guy at the end. What he's doing is he's going to run ammonia gas through the solutions. And as the ammonia gas moves through the solutions, and he actually adds water to the ammonia gas. So now he's got ammonia in solution, right? And you'll watch the color change this direction, and then it'll come back this direction. And you can see it as it happens, and you can see the way the liquid's moving, and it's actually it's really cool. Like I was impressed. Great experiment. I wish I had enough flasks to do it myself. I don't know. By the way, I think it's like a
512 students.
4-liter beaker. It's huge.
Mr. Pinar and I have set up this demonstration for you to give an illustration of indicators and look at some properties of both ammonia and its influence on universal indicator. So Mr. P and I, what we did is we set up this apparatus, and all of these bulbs are connected to each other through these glass tubes. So it's essentially like one chamber. But we've got obviously these different locations of volume. What we did is we flooded the chamber, starting with the with this over here with ammonia gas. We produce the ammonia gas through a reaction, and the ammonia gas is getting lower and lower in concentration as we move over here to this final bulb. In the big beaker, we have
Big is an understatement. It's massive.
polarity of 2 molar acetic acid
Oh,
and
yeah.
about 1,500 mils of water.
If
And
that's
we've got
1,500.
a universal indicator in there as well. So you can see
Maybe
the
more.
color that
It's
is
huge.
coming as acidic. So what I'm gonna do now is I'm gonna add a small amount of distilled water up to the top. Just that right now. And I'm gonna open. So right now it's closed, let it in the water. And then I'm gonna close out quickly.
You could hear that gas escape. So now you got a little vacuum at work too.
Now I'm gonna do, holding up pH scale here for the various colors. You need to take note of what color each one of the bulbs is. So you have that red beginning, pretty green. This one's blue. This one's a deeper purple color. This up here is pretty much the same color as this bulb here. So now what I'm gonna do is I'm gonna open up the valve again. And we'll see what happens.
Now your vacuum's gone and you got the opposite effect, right? So now gravity's working and he's gonna speed it up because it takes a while for gravity to make this work. But you can watch the color change. It's so pretty. It really is. Now watch the beaker too. Interesting, because you can watch it shift the whole time.
So what started out as a very low pH at the beginning of the acetic acid, started out with a pH of maybe 0 and 1. Is now gotten to a pH of approximately 10 or 11 in here. As the ammonia essentially was dissolved, okay, and has created the alkaline environment.
So cool. I think he's Canadian based on that accent, or maybe like Wyoming or something, very far north, because he said again and throughout, you know. But he tells you here how he generated the ammonia gas. He did sodium hydroxide and ammonium chloride and heated them up. And then the acetic acid, which is vinegar, right, was prepared by diluting 30 mils of 2 molar with 1.5 liters of, look, DH2O. That's your distilled or deionized. That's where that comes from. Sometimes you'll see that. So titration, concentration from volume to amount in moles. So how do we do these problems? It takes 83 milliliters of a 0.45 molar sodium hydroxide solution to neutralize 235 milliliters of a hydrochloric acid solution. What is the concentration of hydrochloric acid solution? So did anybody attempt it? Y'all are like chickens. So this is what you would use. Okay, this is the formula of what you would use. And this is not going to be on your test, but you will have an ideal gas law equation on your test. So this would be how you would work it out. So if you did attempt it and you got about 0.16 molar hydrochloric acid, that would be the correct answer. And you will use this equation when we do our titration in a couple weeks. So not the end of the world, though. You can do it. So equilibria of weak acids and bases. The strength of an acid can be measured by the fraction of the acid molecules that do what? What do we want them to do? Strong bases have, yes. There you go. Yes. That, there we go. That undergo ionization or lose a proton, which is dissociate, which is exactly correct. So some acids are going to be better proton donors than others. So strong acids are those that ionize completely in water. That is, they give up their, what do they give up? Protons, everybody. Yes. Strong acids are better proton donors. Here are some examples of strong acids. We've used this one a bunch already, right? We've also used this one. We've used sulfuric and we've used hydrochloric. So you're familiar with both of those. Some bases accept protons more readily than others. A strong base is the converse of a strong acid, whereas an acid is considered strong if it can readily donate protons. A base is considered strong if it can readily what? Accept those pronouns or depronate, remove the H+ ion from other compounds. There you go. So here are some examples of strong bases. We've used sodium hydroxide in lab. We haven't used any of these others, I don't think. No, I don't think. But those are some examples. Now, relative strengths, and here's where we talk about conjugate acid, conjugate base. So if your acid is hydrochloric acid, which is the strongest, its conjugate base is the chloride ion, and it is weak by itself. So what do you think you're going to see when you get down here as far as strength goes?
I know it's strong.
There you go. All right, so sulfuric acid. Anybody know the conjugate base for sulfuric acid? You take away the H. If we took away the H from HCl and we just got a Cl negative. So in this case, we have H2SO4. We need to take away an H. So what are we going to have left? You have H2SO4 and you take away an H. Xander? Be brave, people. There you go. HSO4, now it's negative because you've taken a proton away, and it's the hydrogen sulfate ion. So then what's this one going to be? HNO3 is nitric acid. What's the conjugate base, Colin? NO3 negative. Very good. That's nitrate. Excellent. All right, now let's look at weak acids. H3PO4, which is phosphoric acid. What is the conjugate base going to be? Xander. H2PO4 negative, right? Because you've taken that hydrogen away, that proton is gone, right? And that's dihydrogen phosphate ion. Okay, now if you have CH3COOH, acetic acid, okay, now we got 4 H's in here. We got to get rid of one. Anybody want to guess which one we're going to get rid of?
Alone.
The lone H out by himself? Do you think we're going to have a CH2COOH negative or a CH3COO negative? What do we think? The latter, the first, we don't know. Ah, very good. We're going to get rid of that guy. He's just going to be easier. It's just that he's easier to remove based on the
It's less important.
configuration of that particular compound. Yeah. And so interestingly, you go from acetic acid to acetate. That's acetic acid. That's vinegar, right? And now we have an acetate ion. How about H2CO3 carbonic acid is going to be what?
HCO3.
HCO3 what? You've taken negative, HCO3 negative. So that's your hydrogen carbonate ion. And then lastly, HCN, which is hydrocyanic acid. What's going to happen here?
Death.
What do you think?
Death.
You could be both of you are right. And why are both of you right? Because that is what? CN negative is cyanide. And it's going to be your strongest conjugate base. So death, yeah, it could be death if you ate it. Yeah, if you don't want to eat or drink cyanide, right? So there you go.
Tastes like cyanide.
Do what? No, it's not on my list of
That's
things
not
I've
what you
tried. You curious? Knock yourself out, just not at my house. I don't want to be responsible for it. We could make some cyanide, but I don't think we're going
All
to.
you need to do is like grind up at least 2 cherry pits.
Yeah, apple seeds and cherry pits and all that. They do
Well,
have
apple
some
seeds,
cyanide.
it's like from 100 to 1,000.
Yeah, you need a lot of
But
them.
for a cherry pit, someone too.
Yeah, is it two? I don't know. Yeah.
I've done my research.
Ah, I think it takes more than 2, but still. So the acid ionization constant, what is this? So the acid ionization constant, we show it as Ka. So if you were to do the equation, you're trying to figure it out, your Ka. So here's your proton, right? And then there's lots of, we're not going to do these calculations, but here's the way to remember them. Ice, isn't that easy? And it's, whoops, hang on, wait. Oh. You're going to show me? Initial change equilibrium.
Do it for life.
That's what you need to know to do the calculation. Oh, what is that? Oh, it's weird ASMR commercial. Freaking me out. Stop it. Go away. What?
First, we'll learn the difference between a strong and weak acid and base.
You've seen worse at the beach.
How to write a dissociation constant expression. And then
Lord
find
have mercy.
a sample problem in order to use those dissociation
Diddy party.
expressions.
Yeah.
So first, the difference
About
between
right.
a strong and weak acid. When an acid or a base, we could also say a base, dissociates or dissolves in water, it's gonna split apart, and for acids, they're gonna split into hydrogen ions. And then some kind of anion, something with a negative charge. And so hydrogen ions have a positive charge. If an acid or a base is going to be strong, it means it's gonna dissociate 100% or completely. So for an acid, we would have all of our acid molecules here put into water, and as they dissolve, they would all split apart. And we get all these free ions floating around in the solution. And so that gives us 100% of these acid H plus ions, which makes an acid. For a weak acid or base, only some of those particles are gonna split apart. So with our weak acid, maybe only one of these will actually split, whereas all the rest will stay together. And so we don't get as many of these H plus ions as the strong acid. With a base, we're not concerned with H plus, but we're concerned with hydroxide, this ion right here. This is what makes a base a base. And usually we have some kind of metal, this is sodium that's attached to that hydroxide, and so when it dissolves or dissociates, we're gonna end up with the metal ion, which doesn't really do anything as far as making something acidic or basic. And then we have that hydroxide, and so the more hydroxide ions we could get into solution, the stronger the base is going to be. So we can determine how strong or weak an acid or base is by calculating the dissociation constant. Now, the smaller the dissociation constant, the weaker the acid or base is going to be. The dissociation constants are going to be based on the way that these substances are going to split apart or dissolve. So we'll start with this one. This is hydrochloric acid, which is a strong acid. When it breaks apart, we're going to end up with the hydrogens splitting apart from the chlorine. And so we'll get this kind of thing in solution. So the dissociation expression is going to compare the amount of stuff that split apart to the amount of stuff that remained whole. And for acid, we use the symbol K sub A, and this is the dissociation constant for an acid. And what we do is we take the concentration of the two products, it's these things over here. Generally, it's always going to be H plus and some anion. So we'll take the concentration of the hydrogen ion times the concentration of the anion, and then we divide that by the concentration
Hold on, it seems laggy for a second. Load.
of the reactant, which is the thing that we started with. So we're comparing how much of the stuff split apart, the stuff over here, to how much remained intact. And so the bigger this number, and the biggest we would get is 1, but the bigger this number, the stronger the acid is going to be. Here's another example below this, and this is called acetic acid. It's a little bit different looking, but it works the same way. We're just going to take off one of these hydrogens. This is a weak acid, so it will not dissociate completely. And we'll end up with the anion here and a hydrogen ion. And to write the dissociation expression, we would take these products and divide by the reactants. And then finally, we have a base. And in this base, we have a sodium and a hydroxide. They're going to split apart, and we'll end up with the sodium metal and a hydroxide ion. And since we're dealing with a base this time, we're going to use the symbol K sub B. And we'll do the same thing where we take the products, that's going to be the concentration of sodium compared to the concentration of hydroxide, and divide that by the concentration of the thing that we started with. So let's go ahead and try calculating one of these constants. So this problem says a 0.1 molar solution of acetic acid has a hydrogen ion concentration of 1.32 times 10 to the negative 3 molar. And it says, what is the acid dissociation constant? The first thing you want to do when you're solving a problem like this is write out the dissociation chemical reaction. So this is acetic acid, that's the chemical formula for acetic acid. And this is going to dissociate into H plus and the anion, just like that. So we'll start with that. And what we want to do is we want to look at the initial concentration of acetic acid, what we started with, that's gonna be this amount right here, because we started with 0.1 molar solution. And so this represents before this thing is dissociated at all. So this is our initial, that's what I stands for. And these are both gonna be 0 because nothing's split apart yet. Next, we'll look at the change, how this is going to change. And we'll represent that by SC. And the hydrogen ion concentration is gonna change from 0 to 1.32 times 10 to the negative 3. Now, based on this chemical reaction, the stoichiometry here, it's a 1 to 1 to 1 ratio. And that's looking at the coefficients in front. If there's nothing there, that just means there's one of those substances. So if this goes up, it's increasing by 1.32 times 10 to the negative 3. This has to go up by the same amount because it's a 1 to 1 ratio. Now, since this stuff is splitting apart, the acetic acid is splitting apart to form this, every time one of these splits apart, this is going to go up, which means this has to decrease. So as these go up by 1.32 times 10 to the negative 3, this must decrease by the same amount. Again, it's a 1 to 1 to 1 ratio. So we have these parts going up, I can say plus, and then this part decreasing. Finally, we'll see how does it change or what's the result. We call this the equilibrium. And so this is commonly called an ice chart, the thing that we're creating here. So it's the initial amounts, the change, and then the equilibrium. All we do is we look at each column and we just do the math here. So we'd have 0.1 minus 1.32 times 10 to the negative 3. Then over here, we're just adding that amount. Now, when we plug in the information into our equilibrium expression, it's the amounts at equilibrium that we're concerned with. So we always have to start with this given information and then decide how much is everything going to change by. The equilibrium expression for this is going to be the concentrations of hydrogen times the concentrations of this anion over the concentration of the original acetic acid. And now I can just plug in all the information from my chart and then solve for the Ka. And I end up with a Ka that's going to be equal to 1.77 times 10 to the negative 5. And so there's my acid dissociation.
If you have to calculate
constant
one,
for acetic acid.
that's how you do it. I'm not gonna make you do it on the test. But here's the great thing. We already know some of these. It's already done for us. Look at that. There's the Ka. It's a known value. We've done it enough times that you don't have to necessarily do it every time you're working with those chemicals. So these are constants, ionization constants. And some of my favorites, I think my absolute favorite is right here when you have hexa-aqua aluminum ion. And then over here on this side, your conjugate base is penta-oxo-hydroxy aluminum ion. These are great names. Pentahydroxo iron ion. Some of these are really fun, like really, really great. So that's how they get these numbers. So if you ever have to use these numbers, and you may do a lab in college or whatever, where you have to use these numbers and you're wondering where the heck it came from, that's how they get to it. All right, so buffers. Now we're on to buffers. We mentioned buffers briefly when we're talking about how to do a titration. Here's the deal with buffers. So what did I say a buffer solution was? It does what to the pH? Yes. Kind of. Yeah, it resists a change in pH. So when you add acid or base, it resists the change in pH. So it's able to neutralize small amounts of acid or base, thus maintaining the pH of a solution relatively stable. It's an important process and or for reactions which require specific and stable pH ranges. It has a working pH range and capacity which dictate how much acid or base can be neutralized before the pH changes and the amount by which it will change. Buffers have two ingredients: an aqueous solution containing a weak acid and its conjugate base, and an aqueous solution containing a weak base and its conjugate acid. You mix these things together, you create a buffer.
In this online lecture, we're going to discuss buffer solutions. And what we want to know about a buffer here is that first, they resist changes in pH. We're going to see two, buffers are made up of a weak acid and its conjugate base most of the time.
Or a weak base.
You can also make up a buffer by a weak base and its conjugate acid. We're also going to see three, How the buffer resists changes in pH, it does it by the weak acid consuming any hydroxide ion added to the solution, and the conjugate base consumes any hydronium ion added to the solution. So let me show you how that works here. Let's say you have a solution that has a buffer. Here's our weak acid HA, and here's his conjugate base A-. Now, how is it that these two species resist changes in pH? Well, remember, one way to change the pH is add a strong acid or pure H+ into the solution. Let me show you what happens here. After this is added in here, then the A- combines with that H+, and think about it, the A- is attracted to the H+, and what happens is it comes together and makes HA, which notice happens to be our weak acid of our buffer. But the key point is think about it this way. The A- is almost like vacuuming up all the H+ that's added and converting it into HA, therefore removing H+ from the solution. Now, remember, that's not the only way to change the pH of a solution. You could also add a strong base or pure OH-. In this case, it's the HA of the buffer that takes care of the OH-. Since he's a weak acid, what he does is simply protonate the oxygen of the OH, turning that into water, and as a side product, we're also getting A-. In this case, HA is vacuuming up all the OH- that gets added to this solution, therefore removing OH from the solution. This in turn means that the pH will remain constant for this solution. Now, keep in mind, buffers have a limit. It depends upon how much HA and A you have in solution. For instance, if I keep adding a bunch of H+ and I run out of A- to combine with it, then at that point you have exhausted your buffer and the pH will now start to change. So what have we learned here about buffers? Key point number 1, that they resist changes in pH. And number 2, they're made up of a weak acid and its conjugate base, or it works just as well with a weak base and its conjugate acid. And we also saw how they resist a change in pH, and that is the weak acid consumes any hydroxide ion added to the solution, and the conjugate base consumes any hydronium ion added to the solution.
So buffer solutions are going to stabilize pH, and that's the whole point. Sometimes you need it depending on what you're doing. So they're everywhere. You may not have realized this, but buffers are part of your daily life. Yeah.
They're in shampoos and.
Yes. They're also, yeah, they're in your, yeah, exactly. They're in your blood. So an example of a biological buffer is you have buffers in your bloodstream that maintain your roughly 7.4 pH level, which is specifically carbonic acid and hydrogen carbonate. That's the buffer that exists in your blood. You've also got buffers in fermentation process for beer, for example. They're placed in before the fermentation so it doesn't get too acidic. If it gets too acidic, it might mess up the fermentation process because it could destroy the yeast. So buffers are used in shampoos to balance out alkalinity that would burn your scalp. Bases burn. Remember, bases can burn. So if you look at your shampoo and you see things like citric acid and sodium hydroxide in it, like some people will look at that and be like, why are there so many chemicals in my shampoo or whatever? Well, this is why. There's a reason for it. That's exactly why they're there. And then another good example is baby lotion. So baby lotion has a slightly acidic pH of 6. And it inhibits growth of bacteria. That's why like the new wave deodorants like the Carpe and the Lumi and the Mando are all acidic because it inhibits the growth of bacteria. So if you use one of those deodorants, a lot of them come in like lotion form, but if you rub that in your pits, it's going to make it slightly acidic in there. The bacteria doesn't grow as well. You don't stink, instead of just like how they used to put aluminum and stuff in. So getting this pH where you want it and keeping it where you want it, you can add a buffer. All right, so why is the steepness of a titration curve helpful in locating the equivalence point? Anybody got that one? Nope. So steep titration curve implies that the pH changes very rapidly near an endpoint. So precise volume can be measured with little uncertainty. So if you're looking at it on a graph, you're gonna come up and you see, oh, here's my equivalence point. This is where I'm starting to see a color change. There's my end point. The color's changed and it's not changing anymore. And that space in between is where you have your pH shift. That's your indicator. It's your indicator zone. It's range. Write all 3 Ka expressions. Did anybody try this? So they look like so. And if you care to go back and there's a whole video here for them, I'll skip it for now. But if you want to watch how to do it, there's a whole video for how to do it exactly. So in preparing for titration, explain why cleaning burettes and eliminating air bubbles are important. Okay, we went over it. Who wants to summarize for me?
They can affect measurements.
What does?
The air bubbles.
Bubbles affect measurements. Jordan?
It's so precise that even just the ions in tap water could be enough to know.
Yes, so you have to clean it out and get the ions and tap water out. And why do you have to rinse and purge the beaker with your titrant before, rinse and purge the, what's the word around? Burette with your titrant before you use it. Get rid of any remaining water. You've got it. So the burette should be properly cleaned to ensure no contaminants are present. Air bubbles add to your volume, right? Right. All right. In a 0.25 molar solution of formic acid, the hydronium ion concentration is 2.03 times 10 to the negative third moles. Calculate the Ka for HCOOH, formic acid. Did anybody try? Oh, y'all are, a lot of y'all are chicken with math. I've had some that chomp at the bit. They're like, oh, math, I'm doing the math. This class is not the mathiest class I've ever had. Yeah, Alex loved the math. Not the mathiest class I've ever had. So this is what it would look like. Da-da-dum, 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 and you'd get to here. And you can go back and review this if you want. This is not on your test. It will be when you get to college, I promise. If you take chem in college, they will make you do it. All right, so I love this. This dude here is Francois Antoine Henri de Croisilles. And he's credited with inventing titration. What year do we guess? What year for titration? Liam, what's your guess?
1843.
Here's what we'll do. Closest without going over. Remember your number. 1843, Ridley. 1824, Lucas. 1820, Xander. 1830, Jordan. 1783. All right, Colin. 1818, Drew. Pick another year, Drew. 1810, Caitlin. 1790. What did you say, Luke? Who said 17 something over there?
I said 1783.
1783, 1790, yeah?
1897.
1897. You already guessed.
What was mine again?
You guessed 18.
1844, yeah, I think.
That was 1845.
1795, 1877, 1900. No guess. James, you got a guess? Mm-hmm. 1786. He's looking at the clothes, aren't you? Gabe? 100 BC. 1795. Oh, did somebody say 1794? You said 1790?
Really close, yeah.
You were 1790 what, 4?
I was 1783.
1790. So 1790, Caitlin wins. Caitlin's closest. All right. All right. So it he was the first to assemble a titration apparatus, though not in its current form. Now, a couple of weeks ago, I told you who invented the burette. Actually, I didn't tell you. A really goofy video that rapped about some guy and said that he didn't get as much props as he should in history. Do we remember who that video was about? It was a gas law guy. And I'm like, what are they talking about? He has a gas law named after him. I think it was in the class that we had to go virtual for, I think it was.
Gay-Lussac.
It was Gay-Lussac. Very good. Okay, so Gay-Lussac invented the burette. So yeah, Gay-Lussac invented the burette. So Carl Friedrich Mohr is considered the father of modern titration. He redesigned the burette. So if you can remember anything about Gay-Lussac, and then of course this was 1795, this guy had his first apparatus. So he's gonna redesign the burette to make it simpler and more convenient to use. So what year do you think he got all this done and wrote a textbook? Okay, closest without going over. All right, Xander. 1872. Jordan.
1890.
Okay, Colin.
1818.
All right.
1853.
Yep.
It's gonna say 1850.
Okay. Lucas. 2025. For sure not. I was doing this in 1990s in college, so for sure not.
Going over.
1855. So who was
I
closest?
didn't get the guess.
Who really? 1855. All right. So in 1855, he wrote the first textbook on analytical chemistry using titration methods. Look at his name. Anybody want to guess what the book is called based on his name? Where do you think he's from?
Germany.
Okay, good guess. Yeah. So what do we? Anybody want to imagine what that might be titled in German? I'll just tell you. Woo! That's a fun one. Lehrbuch, because bees, yeah, Lehrbuch, der Chemik, Analytischen. Fun, right? Yeah. All right, this was a fun one. You can do this at home. You can absolutely do this at home.
The one thing that would be better is carrot.
Carrot, yeah.
Hey guys, welcome back to my group. Today we are gonna do some.
I love how he disses on red cabbage. Too. It's kind of funny. Creepy channel. I don't know why.
You must have learned in school about acids and bases, also called as alkali. To know if a solution is acidic or alkaline, people use something known as an indicator. They come in paper form known as litmus paper or a liquid solution. It changes color differently when it meets an acid or an alkali. They are sold at laboratory supply stores, but today I'm going to show you how you can make your own at home from red cabbage. I know it's purple, but it's still called red cabbage, so deal with it.
I love
Take a
that.
couple
It's
big
purple, but
leaves
deal with
from the
it.
Cabbage and put it in a blender. Then add about 3 glasses of water. Distilled water is preferred at this point, but even tap water will work. At least that is what I'm using. Now blend it together until you
24
end up with
ounces.
some healthy cabbage juice.
So it looks like soap.
Delicious. Yum.
I'm gonna drain it first.
You
using
drink that, you'll fart for a
This is
year.
gonna take a while. I have to get rid of all
You
the
will.
starch.
Yeah, tea strainer.
Next, I'll filter it through a piece of cloth to remove any small pieces of cabbage left behind. With this, our universal indicator is now ready. Now we need some solutions to test. The measure of acidity or alkalinity is done in pH value. The pH scale has 14 increments. The lower the number on pH scale, the more acidic the solution is. And
That
the
is
higher
not
the value,
aligned
the more
properly, but
alkaline the
okay.
solution. And 7 is the neutral zone.
Those like 8.
Here are 7
Yeah.
commonly available solutions which we are going to test. Lemon juice, vinegar, carbonated lemon soda, water, toothpaste and water solution, baking soda and water solution, and finally bleach. Now I'm going to pour my indicator into the glasses to see what happens. The lemon juice, being the most acidic of the lot, changes to a bright red color. The vinegar changes to a pink or a less bright red color. The lemon soda changes to pink shade.
Beautiful.
The water, being neutral, takes the color of the indicator and becomes purple. The toothpaste and water solution changes to a blue shade, which means now we have stepped over to the alkaline zone. The baking soda and water solution turns a bluish green shade. And finally, the bleach, being the strongest base of the lot, dissolves the purple color completely and
Bleach.
retains its own light yellow color.
No
You
color
can
from the
see
bleach.
It's changed color in all the different solutions. This is a very fun and easy experiment you can try at home for almost free, and it is also an excellent and safe way to demonstrate the concept of acids and bases to kids. Now, I was also told at school that acids neutralizes alkali and vice versa. So that means if I mix the solutions at the extreme ends together, they should cancel out each other and I should end up with purple color. So let's try it. When I mix the lemon juice with the bleach, there is no effect on the color. The bleach is a much stronger base than the lemon juice is an acid. It will require a lot more of juice to neutralize the alkali completely and turn the color back purple. Next, when I mix the vinegar and baking soda, there is a sudden release of carbon dioxide gas and the whole solution foams and spills over the glass. It is still not completely neutralized, so it is holding on to the pink color, showing that it is still slightly acidic. Finally, when I mix the lemon soda and toothpaste solution, both being a weak acid and a weak base, neutralize each other completely and we get perfect purple color, same as the water solution. You can also try it out with other solutions to see what you get, and do let me know how it goes in the comments below.
This cracks me
Before
up
I go,
too.
I'd like to remind
Why
you
you
that
put this in a
selfie
YouTube
drone
video?
giveaway is still going
I'm
on
sure it
and
is
will
not
be
still going
announced
on.
soon. Take part in that giveaway.
Video is years old.
The link is going right now.
He said it's still going on, but I don't know why. Okay, here's your stuff to know. Q4 begins next week. So that means that you got to look at your Q3 grade book for anything that is missing. Some of you still have missing things. The day we had to cancel class and go virtual, a lot of you don't have class participation for that, for example. You're supposed to comment. I don't have comments from everybody. So I'm giving you till the 10th, which is essentially a week in to your Q4 to get all this work done. Okay, so please be sure you get it in by 8 a.m. on 310 or it's a 0. No excuses. Everybody understands that, right? Get your work. Look at it. I'm not going to remind you 400 more times. Like you're going to get this reminder and there's a reminder in your email. And that's all I'm saying. I'm not going to come up to you and be like, you have like 5 assignments outstanding. Some of you have a lot. Some of you have labs you're missing. Labs will ding the heck out of your average, y'all. Like for real. Don't do that. Don't do that. All right. Now this is an important reminder. Just a reminder. We are still in priority enrollment right now. January 15th through March 30 is priority enrollment, and open enrollment begins, February 28th. So January 15th through February 28th. But March 1st is a Saturday, and March 1st open enrollment is going to open up, and I cannot save your seat. So if you intend to come back next year and you don't find yourself on this list, you need to go home and remind mom or dad, because I've sent multiple reminders. So if your name's not on here and you plan to be here, go home and be like, yo, mom, don't forget, Friday's the deadline, because otherwise I cannot save your seat. Last year we had 8 people on a waiting list. Now, if you look, there are 7 of you who aren't seniors that I haven't heard from. Actually, it's 6 because I did hear from 1 that's not coming back. So 6 of you I still don't know about, but I only have 9 seats left. So if you wait, I'm not going to have your seat. It's going to disappear. I want you to come back, but I won't be able to seat you because I will have people on a waiting list. So keep that in mind. Now, the fun part. Here we go. Look at that first one there. Using ideal gas law to calculate volume when given molarity, temperature, and pressure. What is the ideal gas law equation?
PV and RT.
P equals V. PV equals nRT. There it is. Yes. So you need to know your PIV nerd, right? Your PIV nerd. Real quick, right here where it says different ways. Listen. Different ways to define acids, bases, and the reasons for those. What I'm meaning by that is Arrhenius theory, Bronsted-Lowry theory, and Lewis theory. Arrhenius theory focused on what ions? What mattered to him? Do you remember? Hydrogen and hydroxide. Arrhenius said your acids have your hydrogens, your bases have your hydroxides. Then we had Bronsted-Lowry, and they focused on what? Well, they focused on proton, who accepts or donates protons. That's your Bronsted-Lowry. And what did Lewis focus on? Not protons, but electrons, who donates or accepts electrons. Why do we have 3 different theories? Why was Arrhenius not good enough? And then we had Bronsted-Lowry, and then why?
Donor donates the electrons and the receiver takes the electrons.
Alexa. Shush. That was fun. I don't know what she heard that made her do that. You need to be able to explain to me why Bronsted-Lowry had to revise Arrhenius, and then why Lewis had to add to Bronstead Lowry and revise it with his electron bit. Why wasn't Arrhenius just good enough? So we talked about it, I think, last week. So go back and look at your slides, do whatever you have to do, but that's where we are with things. Okay, good. We wrapped up 10 early. You don't have to rush out, but if you want to, you may. Yes, sir.
Consecutive questions. I was like, and.
Where are you talking about? Oh, for your homework or something from last week? You started it but didn't finish it. Because there was what? It looked weird. It was in your.
Yeah, it was like Oxford and.
That's weird, because not everybody had that, so. Let me see if I can find it. Yes, sir.
It's gonna be Lucy's final year.
Okay, I'm sorry to hear that. I'm gonna miss you guys a ton. Lucy said this morning she was going back to public school. Is
Yeah,
that
we're
y'all?
gonna.
Okay. I will miss you.